There's the video recording. Okay.
Can you put that on Canvas too?
Yes. Well, I've been putting it on the schedule that I sent out to you. I added links to my YouTube channel and the notes that I wrote up, because I don't know if Canvas isn't the old Canvas class that you were in, like, might not be pinging you anymore. Or, yeah. Okay. That's fine. You don't have to actually follow me.
I'm disappointed.
Did you like, comment, and subscribe on my YouTube channel?
I did watch some of the other videos though. The one with the one with the that the color changed to the water. That was
Oh, that was from the times we don't talk about, when I taught on Zoom from my old living room that was also the dining room and the kitchen of my old apartment I used to live in. And I had the gas tube. Fun stuff.
Disappointed.
Okay.
Show us Bennett at the end of one of the Saturday sessions.
Yeah, we should.
Oh, sure, yeah. I can, that's fine. Just remind me.
These are actually good Saturday.
Okay. Equilibrium. Let's talk about the chemistry things. It's when you have a reversible reaction, which is most of them. Something like this. Actually, let me write it with coefficients. Here's a reaction equation. So remember the double arrow, the double-sided arrow means this reaction is reversible, which a lot of processes are. So the reactants are turning into products, and the products are also turning back into reactants. At equilibrium, when the system is at equilibrium, the rate of the forward reaction is the same, equals the rate of the reverse reaction. Reverse reaction. And from Unit 5, the rate, you could write the rate laws if you want. The rate at which the products form is the same as the rate at which the reactants form. Both reactants and products are present in your system. Are present. At equilibrium, your system is sitting there, and at the macroscopic scale looks like nothing's going on. But at the microscopic particle level, it's a dynamic equilibrium. There's always like A and B colliding to make C and D, and there's always C and D colliding to make A and B. But if the rates of those processes are the same, then at the macroscopic scale, it doesn't look like anything's changing. So the concentrations specifically is what isn't changing. Concentrations, or if you have gases, it could be partial pressures. Those are constant at equilibrium. So in a graph, maybe I'll switch to blue because I don't like that black. It's kind of dull. You might have concentration versus time on a graph. Might look like this for your products, and this your reactants. So your products would start at 0. You would start with all reactants, and then over time the reactants start turning into products. So the reactant concentration goes down, product concentration goes up, and then once they level off and the slope is basically 0, that would be considered equilibrium. Equilibrium from this point forward on the graph. So this would be an example where at equilibrium, the concentration of products is higher. So you would say the products are favored in that example. You could also have a similar graph that would look like this, where you would end up with just a little bit of product and mostly reactants, products. So again, it levels off some point here at equilibrium, but in this example, even at equilibrium, it's still mostly reactants, so you would say the reactants are favored in that example. Okay. So, number-wise, math stuff. Equilibrium constant, capital K. Capital K. This is the equilibrium constant. The expression for that looks like this. It's a fraction where the products, C and D, those concentrations go on the top, and you do use the exponents from just the balanced reaction equation. You use the coefficients from the balanced reaction equation as the exponents there on the concentrations. And then your reactant concentrations go on the bottom. So like that. And if you're using concentrations, that is actually usually called Kc for concentration. You could also have a Kp, and that would be using partial pressures of the different things. Pa to the A, B, B, B. So that's, if you have everything as a gas, partial pressures of the gas. One thing that they like to try to trick you on in the AP test is having you write an equilibrium expression for the equilibrium constant. And don't just go apply this willy-nilly, because you might get caught in the trap, which is that if you have a pure solid, which they would tell you with the state symbol parentheses S, right? And pure liquids are not included in the expression for the equilibrium constant. So only aqueous solutions, in which case you would use the concentrations, and pure gases, G, in which case you would use the partial pressures. Yeah.
By pure, do you mean like an element? Sorry.
Like an element or a compound, not a mixture. Like an aqueous solution is a liquid, or it looks like a liquid, but it's not pure, because it has stuff dissolved in it, that the concentrations would be changing.
Okay.
Okay.
Maybe we can put that back on.
Okay, so let me hit you with a quick example, just instead of saying rules. Go back up top.
Oh yeah, that's great. Except we do it all day.
It was beautiful.
Yeah.
Oh, you know Jubilee-Doo?
Yeah, that was the
You
best
follow
part
the
about
Brothers
it.
Green?
The description.
Yeah, the video description.
Yeah, it was
It made me cry.
Okay, examples. Say I have this reaction, 2KClO3 solid, double arrow, 2KCl solid plus 3O2 gas. Okay, kids, what's the equilibrium expression for capital K? Don't get caught in the trap. You don't include the solids. So the fraction, nothing goes on the bottom of the fraction. So it's just the concentration of O2 and to the power of its exponent there, 3. That's it. Okay, you don't include the solids. Okay. You can do manipulation of equations with the equilibrium constant. Manipulating equations with capital K. Here's the rules. let's say I have this example, A, that's a solid, plus 1/2 B2, that's a gas. Double arrow makes AB, that's a gas. And say I have a K that's 2.3 times 10 to the 3. Uh-oh. My computer looks black. What happened? Am I still recording? Oh, yeah, okay. Just timed out. This is a relatively big value of K. That means the products would be favored. So you would have more AB at equilibrium and not very much reactance. If I want to manipulate this, if I multiply the whole reaction by 2, say, 1/2 times 2 is just 1, goes to 2AB as a gas. This, I multiplied my reaction by 2. What happens to K? It gets squared in that example. So the K for the reaction that's been multiplied by 2 is the square of the old K. So that would be, if you work it out, about 5.3 times 10 to the 6. This is different than the rules for the rate constant. So the rate constant would just multiply. The equilibrium constant squares. It's all multiplicative with the equilibrium constants. If I reverse that reaction and put the AB in the front, so from my original reaction, AB, gas, double arrow, A as a solid, and 1/2 B2 as a gas. Just from the definition expression for K, I'm reversing the products and reactants, which means I'm reversing the top and bottom of that fraction. So this goes to 1 over K. If I do reverse reaction, it would be 1 over 2.3 times 10 to the 3. The reciprocal, in other words. So you would get, if you did that, 2.5 times 10 to the minus 4, according to Adrian Dickel. This is 1 over the original value of K. All right. All right. And if you're adding steps of a reaction to get a different reaction, the K's multiply. So let me do a quick example of that. Bottom board. Yep.
When you reverse it, why does it go from 2.3 to 2.5?
Because I'm taking the reciprocal. So take 1 divided by this number. I don't know. That's what the book says in the book. No, because it's 1 over this whole thing. 2.3 times 10 to the 3. Is that wrong? Maybe I read it wrong.
Would that be 1 over what, 23,000 or 2,300?
2,300? No?
I get something.
Maybe I'm writing the wrong line.
It gets
Go
to
too
like
fast.
4.3 times 10 to the negative 4. That's what that gets to.
If the original K. Oh, why did I? You're right. What is that?
4.3 times 10 to the negative 4, I think.
4.3.
Yeah, that's what I got.
Okay, sorry, I was reading the wrong thing. You're right.
Yep, that's fine. Is the
Okay.
other one right? But yeah.
If you square this, 2.3 squared, 5.3, I think that's right. 10 to the 3 squared would give you 10 to the 6.
5.29. Yeah, that's right.
All right. Let's see. Okay, so let's say I know this reaction, carbon or like graphite plus oxygen gas. So solid gas making carbon monoxide gas. And I know the K for that is 2.28 times 10 to the 23. So that's not an equilibrium really that goes to completion for all intents and purposes. So let's call that 1. And let's say we have graphite plus O2 gas making CO2 gas with a K of 1.25 times 10 to the 69th power. So that's even more, like very little reactants. That's a combustion reaction, so the fire just goes until it's done, pretty much. That's why the K's are so big. Say you want to know what the K is for this. How do you make that? Well, if I want CO over here, I have to flip this one, right? And get CO on the left. 2 has CO2 on the right, so that's a product I want. And I also need to double, let's see. If I flip this 1, I need the coefficient 2. So if I flip 1 and double it, flip 1 and multiply it by 2, okay, then I get 2CO yields 2C plus O2. And then my K is both inverted and squared. So my K, let's call this K1 and K2. My new K for this is going to be 1 over K1 squared. Right? And so 1.92 times 10 to the minus 47 is the number you would get for that. So that gives me this. But I need my CO2 product. Okay. And I need 2, so if I multiply 2 by equation 2, because I need my product to have coefficient 2 right there. Okay. That gives me the following: 2C plus 2O2 makes 2CO2. Okay. And then my K for that equation is K2, but it's squared, okay, because I multiplied the whole thing by 2. So that's 1.56 times 10 to the power 138. Oh boy. So let's call this 4 and this 5. I'm trying to find, this is what I want to know. It's a combination of these two reaction equations, 1 and 2, right? To get it, you have to flip this equation, multiply by 2, which is written here. And then equation 2, the coefficient of the unknown equation on the right needs to be 2, so I have to multiply this whole equation by 2, which is what I did here.
The excess 2C and O2 that you don't want. That is like
This 2C and this 2, if I add these together, right, then I have 2C going in and coming out, so I can effectively cancel that.
And so
right?
why don't the 2O2 and the O2? Oh,
So
it does.
2
I thought there was a coefficient of 2 above in the third equation.
plus 2C plus 2O2. That's everything on the left, right? And I get 2C plus O2 plus 2CO2. Okay. So I have one of the two C's cancel, and one of the O2's cancel. So this one cancels, and this makes a coefficient 1. That's the sum, and that's what I wanted to get for equation 3. Yeah.
Do you think it's realistic we'd ever get a reaction with the power to the 138th?
Sure, why not? It doesn't matter. They're just testing whether you know how to find K given the reactions and the other K's. And so K3 is going to be, if I just get it by adding these two, then I get it by multiplying K4 times K5. Okay? Which we got from doing 1 over K1 squared times K2 squared. Okay. And that's how that works.
Wait,
You
so
can
K3
find the
is
number.
1.92 times 10 to the negative 47 times 1.56 times 10 to the negative 138.
Correct. You would multiply this and this. Because just adding those two reactions gives you the overall reaction that you're interested in. Alright? That's it for K. There is also the matter of Q.
I was right and you were wrong. Oh, right. I'm never gonna let that go. I didn't hear what you said, so I'm gonna you didn't say it.
Q, the reaction quotient, is the same deal as K. That's whenever. Your system doesn't have to be at equilibrium for you to say what Q is. It's just, right now, given these conditions, if I plug my concentrations or my partial pressures into this expression for K, whatever I get is Q, the reaction quotient. And if Q is too small, that is compared to K, what I know is the equilibrium constant for this system, then more products will form. I'm gonna close this door. There's some hooligans out there. If the K is too small, I need the K to get bigger, so the top of the fraction where the products are needs to get bigger. So products will form faster, okay? And then if Q is too big, reactants will form, or more quickly. If Q equals K, then the system is at equilibrium. So they might give you a reaction and tell you a value of K and stuff to calculate Q, and then you would have to figure out, is this at equilibrium? Which way will the reaction go based on is Q bigger or smaller than K? There's also Q, you can also get C or QP based on concentration or pressure. You might see that too. Okay.
Thank you.
Cool. All right.
More lows.
We good. Let's talk about Le Chatelier real quick.
5 minutes.
Oh, we got 5 more minutes.
We got 5 minutes. All right. I may record an addendum to this to put up.
Yeah.
Le Chatelier just says, excuse me, when your system is stressed, it shifts to undo the stress. Okay, that's all that says. Nature abhors a change in its equilibrium state. I lost where I was going here.
Take it to like more energy.
Oh, endo-exo is relevant here. So, for example, here's an example. O3 ozone plus O makes 2O2. And these are all gases. Okay, say I know, they also tell me what's my delta H for this reaction. Negative 318 kilojoules per mole of reaction. Okay. That means my reaction is exothermic. So I can write my delta H, if it's exothermic, I can write it as a product, right? Or I can say plus energy here. And that helps me figure out how does the system respond when you heat it up or cool it down, right? Because that's adding energy. If I heat this system up, I'm effectively adding a product to the equilibrium system. So if I add heat, then I'm stressing it by adding products, and the system will respond by undoing that addition of products, which means it takes the products I added and turns them back into reactants. So if I add heat, this system is going to shift to the left and make more reactants. If I remove heat, if I cool the system down, it's going to shift to the right and add more products.
Can you repeat the remove part? So adding.
If I remove heat, if I stick it in a freezer, then I'm removing energy, which is like a product of my system because it's an exothermic reaction. So I'm taking the equilibrium and I'm stressing it by taking away something that's acting like a product. And so the way the system tries to undo that is by making more products to make up for the stress that I introduced. Okay? That also shifts your value of K. Okay? But only the temperature does that. So let me say that here real quick. Only temp will change the equilibrium constant for your system. That might come up, so you should keep it in mind.
Mr. Lodge, what's 2 plus 2?
5.
What's the square root of 9?
Also 5.
Does changing
You're wrong.
temperature heating up or cooling down? It depends on how it changes based on the exothermic or endothermic.
Yes.
It's not universal.
Yes. If delta H is positive, if you have an endothermic system, then you would write the energy as a reactant, and the effect is opposite.
So exothermic energy is a product.
Right. Energy comes out of the system. This is like the change in my system energy is negative when this reaction happens. Energy coming out. Yeah, so keep track of that. Okay. Couple more things with the Le Chatelier principle. Same principle, I'm just going to show a couple more examples. Here's a classic one they love to talk about. N2 and H2 makes 2NH3, that's ammonia, the synthesis of ammonia. I had talked about what happens if you add or remove heat, but what happens if you change the concentration change? For example, if the concentration of N2 is decreased, for example, in that reaction. If you remove some N2 from the system, then I'm stressing the system by reducing the amount of reactant. And the system's going to make up for that by making more of the reactant that I took away. So the reverse reaction is going to be favored, meaning the rate of the reverse reaction is going to be higher than the rate of the forward reaction until the equilibrium is reestablished and the system is done undoing the stress that I introduced by removing N2. Okay. Similarly, if let's say the H2 concentration is increased, then there's too much reactant in my system that I've stressed, and so the forward reaction is going to be favored. The extra reactant I added is going to turn into product in order to reestablish equilibrium. Okay? And you can apply the same argument for the product. If I take away NH3 from the system, there's not enough product. So the way it undoes that is by adding more product, and the forward reaction is favored. if I add more NH3 to this system when it's at equilibrium, then I have too much product. And it undoes that by turning some product back into reactant. Okay? The last thing is volume or pressure changes. Volume or pressure changes. When you have a gas. So let's take, for example, this reaction. 2NO2 gas combining to make N2O4 gas. So this is two molecules joining to make one molecule. And the reverse reaction, the bigger molecule splitting apart into the two halves. Okay. So what happens if, say, I take that system at equilibrium and I put it in a bigger volume? Or maybe it's in a piston and I lift, it's in a cylinder, I lift the piston so now these particles have access to more space to spread out. What happens there if I change the volume? Well, if I change the volume, that means the pressure in that system has decreased, right? I decrease the pressure, and how does a system of gas react to a stress in the amount of pressure? It will shift to the side with the greatest number of moles of gas, which is this side. There's 2 moles of gas here for every 1 mole there. So if the volume is increased, the pressure decreases, system shifts to the side with more moles of gas, or just more particles of gas in the balanced reaction, okay? Because if you remember your ideal gas laws from Unit 3, more moles of gas, regardless of what the particles are, more moles of gas has more pressure. So if I increase the volume of this system and I stress it by reducing the pressure, the system tries to undo that by shifting to the side with more particles, making more particles to build up more pressure to undo my shift of decreasing the pressure. Okay? And then the reverse is also true. If the volume is decreased, you're compressing that gas system into a smaller volume, the pressure increases, and so the shift is towards the side with fewer particles. In this case, it would shift to the right, where I just have 1 mole of gas, as opposed to 2 on the left. Okay. I think the K, A, and B I'm going to talk about in the Unit 8 stuff with pH. Let me just quickly say with KSP, that's a solubility equilibrium. So that's arguably a physical process where you have, for example, NaCl solid dissolving into its ions, Na+, that would be aqueous, and Cl-, that would be aqueous. So we have a special name for the K, the equilibrium constant for that kind of a process, dissolving or solubility, the KSP, where, again, in this case, we're ignoring the solid. So the KSP would just be the concentration of the sodium ions, and that's to the first power, so no exponent. Concentration of chlorides to the first power, that's it, okay? This is a measure of how well does that substance dissolve. And it does depend on the temperature, but not anything else. So a high value of KSP is something that's good at dissolving in water, okay? A low value of KSP is what we would consider insoluble if you see a KSP value. So high, like 10 to the 3 or more, probably is a good measure of that's a high KSP, something that's good at dissolving. Something that's less than probably 10 to the -3, I would say is a low KSP, okay? General rule, If the power of 10 is positive, that's a big number. If the power of 10 is negative, that's a small number when it comes to KSP.